Okay, so Wojiech Samotij will continue his lectures and he speaks about the container theorem.
Hi. So before I start to speak about hypergraphs, I still owe you one proof that I didn't have the time to finish last time. Recall that we tried to compute the number of sum-free subsets contained in the interval 1 through n. And we had an argument there which in the end relied on an upper bound on the number of independent sets in a d-regular graph on n vertices. So let me state the theorem that we wanted to invoke in order to finish the lemma. The proof of the estimate on the number of sum-free sets. It was a theorem which in some version was first proved by Noga alone in the 90s, and then the version that we try to prove is due to Sapozhenko. And there are sharper estimates first proved by Jeff Kahn for bipartite graphs, and then a reduction of Yufei Zhao made Jeff's argument work for arbitrary irregular graphs. So the statement that I'm going to prove is the following. There is a constant C such that for every n vertex d-regular graph G, the number of independent sets of G does not exceed 2 to the power n over 2 plus a constant times square root of log d over d times n. So this is the bound. And this bound now is a fairly easy consequence of the lemma due to Klitman-Winston that we proved on Monday. And so here, to save time, I took the liberty to write down the statement. So let me briefly review it. We have three parameters here, Q, R, and beta. And we're assuming that our graph satisfies the following property. Whenever we take a subset A, which contains at least R vertices, then the subgraph of G, which is induced by A, has density at least beta. So it contains at least beta A choose two edges. And then the conclusion is that the number of independent sets in G of size M is not much more than the number of M subsets of a set of size R. And here the error is this n choose q, where q is the smallest number such that 1 minus beta to the q times n is at most R. So how one would apply it, first we need to choose R, then we compute beta, then we choose the best possible q, and we get this bound. So let's see how it's done on this example. So first technical comment is that we may assume that D is large, because if D is not large, we can just push everything into this constant. Now, another simplifying assumption is that if M, so we're to get the bound on I of G, we're just going to count independent sets of each size M, starting from 0 to n over 2. And if M is small, if M is n over 10, then we can just use the trivial bound, because then the number of independent sets of size M is at most just the number of subsets of size M, which is at most n choose n over 10. And you can believe me that it's at most 2 to the power 0.48 times n. Now, in the complementary case, so if M is larger than n over 10, then we use the Klitman-Winston lemma. And in order to do it, we need to check that a condition of this type is satisfied. So why is it true in regular graphs? So let's take any set A here, and we think that A is of size greater than n over 2, and let's compute the degree sum in this set A. So if we compute the degree sum, so sum over all V in A, the degree of V, since the graph is regular, then this is just D times A. But some edges will stay within A, and some edges will leave A. The edges that stay in A, we count them twice because they have 2 endpoints in A. And the edges that leave, we just count them once. So this is 2 twice times the edges inside A plus once the edges between A and A complement. Now we have the set A complement here, and how many endpoints can A complement absorb? Since each vertex there has degree at most D, this is at most A complement times D. So this is at most twice the number of edges in A plus n minus A times D. And from here we conclude that the number of edges in A is at least twice A minus n times D over 2. Now, so this will give us a non-trivial bound if A will be somewhat larger than n over 2. And here we choose R to be equal to n over 2 plus beta n squared over 2D for some positive beta. This beta will depend on D, and I will choose it later. And now if A has size at least R, then the number of edges in A, it's at least, this is twice R minus n, so this n over 2 is cancelled. It's just beta n squared over D times D over 2. So this is at least beta n squared over 2D. This D is cancelled, so it's beta n squared over 2, and this is at least beta times n choose 2, which is at least beta times A choose 2. Now, so in other words, with this particular value of R and some beta, our graph satisfies this condition. So we can conclude this bound if, in order to conclude this bound, we need to choose Q so that this condition is satisfied. So this will hold. So we now assume that beta is at least 10 over n, and we choose Q to be the ceiling of 1 over beta, which is at most n over 10. And now just compute e to minus beta q times n. This is at most e to minus 1 times n, which is at most r, because r was smaller than, r was slightly larger than n over 2. And hence, the number of independent sets in G. Well, first, we count the ones which are smaller than n over 10. So that's at most n times 2 to 0.48 n. Now, plus n choose q times 2 to the r for the remaining ones. And this is at most 2 to 0.49 n plus 2. I substitute the definition of r, so it's n over 2 plus beta n squared over 2d. Now we have to compute this, so I'll use the fact here that n choose q is at most en over q to the q. Q is roughly 1 over beta, so this is at most e n beta to 1 over beta. So we get here plus 1 over beta times the logarithm base 2 of En beta. And now we optimize for beta. So optimizing for beta, we let beta to be square root of d log d divided by n. And then indeed, if d is sufficiently large, then square root of d log d is greater than 10. So maybe I was a little quick with the computation, so let me just maybe review the main idea. So since the graph is regular, if we take any subset of vertices which is somewhat larger than n over 2, then by this really simple double counting argument, we can prove that A contains many edges. In other words, this condition is satisfied, so we can conclude this bound if we choose Q, which is large enough so that this condition holds. So this condition will depend more or less only on beta, because R is around n over 2. So here roughly we need Q to be of order 1 over beta. But Q cannot be too large, so we cannot take beta too small, because we're only able to count sets which have size at least Q. So that's why we need to choose beta of order at least roughly 1 over n, so that Q is still much smaller than n over 2. And we conclude this bound. The rest is just a fairly simple calculation. Okay, so this closes what we started on Monday. And maybe if you have any questions, then since now we're going to switch gears completely.
So how tight is
So, okay, this is a very good question. Let me uncover the theorem here. So actually what is true is that the number of independent sets of G is at most the number of independent sets in the graph KDD to the power n over 2d, which is 2 to the d plus 1 minus 1 times n over 2d, and this is very roughly 2 to n over 2 plus n over 2d. Now, if you push this argument, then you can get a bound with this n over 2d replaced by n log d over d times some constant. So you can get pretty close, but not quite there. And the proof of this result, due to Jeff Kahn, uses a very nice entropy argument based on Shearer's inequality.
So this improved, so this work, so Kahn's argument is just for the bipartite.
Bipartite, but then there's a trick of Yufei-Zhao which reduces the non-bipartite case to a bipartite case.
So this actually tells you
Yes. Mm-hmm. Yeah, and also if you analyze the argument, it gives you some sort of exact stability. If you know that the equality holds, then the graph G is a disjoint union of disjoint copies of KDD. Yes.
I didn't see where you count the independent sets of signs between n over 10 and n over 2.
This is here. Oh, so if m is larger, then we have this bound, but what I did is I summed over all m. So the first term stays as n choose q, which is here. And the second term, if you sum over some range of m, then it won't be larger than 2 to the r, because we're summing just some binomial coefficients, r choose m minus something.
Did you assume that A is size n over 2? Isn't the size A m?
No, so we're counting just the independent sets of size m, and we have the following bound on every m which is larger than q, and q is not smaller than n over 10. So we can count all the ones which are at least n over 10, And then I sum over all possible m, and I get n choose q plus sum of some binomial coefficients, which is at most 2 to the r. Okay, so actually the topic for today is an extension of this theorem to the setting of hypergraphs. And as motivation, I mean, the first motivation is that this is a fairly nice and useful bound just on the number of independent sets. So it would be nice if we could have a similar statement which works not only in the two uniform case, but also for higher uniformity. And maybe let me give you some history to give some further motivation. So I think I mentioned on Monday that this statement or this argument behind the proof was first originally used by Klitman-Winston to count graphs which don't contain a 4 cycle. Now, why is it relevant? Well, the argument went roughly as follows. They tried to enumerate all C4 free graphs just by building them up vertex by vertex. Now, if you have a C4 graph here, C4 free graph G, and you're trying to add a new vertex V to it, then we're going to choose some neighborhood here for the vertex V. And what does this neighborhood satisfy? Well, certainly no 2 points in the neighborhood can be connected by a path of length 2, because this would create a copy of C4. So one can define an auxiliary graph on the vertex set G where one connects 2 vertices if their distance in the original graph is equal to 2, and therefore the only choices one can make for the neighborhood of V are just independent sets in this auxiliary graph. And hence, sort of implicitly, this problem reduces to the problem of counting independent sets in this auxiliary graph. So when I was a PhD student, together with Yoshi Balog, we worked on a related problem of counting graphs which do not contain the complete bipartite graph KST, where here, say, you assume S is at most T. And when one tries to run a similar argument, so let's try to build them up vertex by vertex, then again, we want to find some neighborhood for V. And now say we try to avoid the graph K33. So certainly we cannot have now here 3 vertices which all share 2 neighbors, because adding this third vertex would create a copy of K33. So here on the vertex set of G, we can now define an auxiliary 3 uniform hypergraph where 3 vertices form an edge if they share 2 neighbors. They cannot share more than 2 neighbors because this graph is assumed to be K33 free. So now the problem of connecting or counting the number of connections reduces to the problem of counting independent sets in this 3 uniform hypergraph. So this was around 2009, and around the same time, David Conlon and Tim Gowers and Matthias Schacht were working on these general transference theorems that I will explain in a second. And this gave us further motivation to pursue this direction to obtain sort of a stronger and more general theorems. And maybe to tell you what they are, let me discuss everything on this motivating example of arithmetic progressions in random sets of integers. So this will be the topic for today. Okay, so let me start with the following conjecture, which is now a theorem due to Erdős and Turan, I think dating back to 1936. So what they ask, or what they conjectured, is that if I take any number k, integer k at least 3, and a positive constant delta, then if n is sufficiently large, n is at least some n0, then every subset A of integers 1 through n, which contains at least delta n integers contains a k-term arithmetic progression, meaning there are numbers x, x plus d, x plus k minus 1d, which are all lie in A. So if I'm not mistaken, the original motivation for their conjecture was the theorem of Schur, sorry, not Schur, but van der Waerden, who proved that if you color the set 1 through n with some bounded number of colors, then if the set is sufficiently large, then in one of the colors you will see an arithmetic progression. And certainly, if you take the most popular color, then it will contain some positive proportion of all the numbers. So this theorem would imply the theorem of van der Waerden. Now, this question turned out to be fairly difficult. And it was proved first in the case k equals 3 by Klaus Roth, I think in 53, then Andre Szemeredi in 69. Sorry, yes, in 69 proved the case k equals 4. So this is k equals 3, k equals 4. And finally in 75, it was proved by Szemeredi for general k. So now this statement is known under the name of Szemeredi's theorem. And so this will be our starting point. But now the question that we're interested in is, what is so special about this set 1 through n? Can we still have an analogous statement if we replace the set 1 through n by something smaller? So what do I mean by that? Let's fix some set R in 1 to n. And then I'll say that R has the k delta Szemeredi property if and only if, whenever I take some subset of R which contains at least a delta proportion of the elements of R, then A contains some k-term arithmetic progression. Now what I ask for, question, are there sets R in 1 to n which have this property? Okay, so first, several trivial observations. First of all, I should only ask for small sets, because if R contains a positive proportion of all the elements of 1 through n, then every set which contains positive proportion of R contains positive proportion of n, and therefore we can apply Szemeredi's theorem. So definitely want sets R which have sublinear number of elements in n. But here there's also sort of a cheap way out. If I take R to be an arithmetic progression of length n0, then arithmetic progression for the purposes of finding arithmetic progressions inside it would behave exactly like the interval 1 through n0, so this is also not what I want. So specifically, in order to avoid such degenerate cases, I would just want R to be set which is in some way generic but small. And the natural candidate for it is just to take a random subset with certain number of elements. So here, question more specifically is fix some m, which is a function of n, and when does R, which is chosen uniformly at random from all m subsets of the integers 1 through n, satisfy the delta k Szemeredi property. And people who asked this question first were Yoshiko Hayakawa, Tomasz Wojiech, and Wojta Rydl in the 90s, but similar questions were asked in the setting of graphs also earlier by Babai, Szymonovich, and Spencer, and also Frankel and Rydl. Now, it's not so difficult to see that such a statement cannot be true for all functions m. This function m needs to grow somewhat with n, and let's see why. So the crucial quantity to look at here is the expected number of k-term arithmetic progressions that one sees in this random set. So let's compute the expected number of k-term arithmetic progressions in this set R. So very roughly, the set of integers 1 through n contains order n squared k-term arithmetic progressions. We just choose the starting point and the common difference. Now, then we then we ask for all these k elements to be contained in this random set of size m. So this is very roughly m over n to the k. Exactly, it's m times n minus 1 and so on divided by n times n minus 1. But for all purposes, this is enough. So certainly if this expectation is little of 1, then typically the number of k-term APs in R is 0. So if to start with we don't have any k-term arithmetic progressions, certainly after we delete some elements here. Now, but one can do a little better if the expectation is much smaller than the number of elements itself. Then we can just keep, say, 99% of the elements and still not have any arithmetic progressions by deleting one element from each. So then R doesn't have the delta k Szemeredi property. Now, when does this happen? So this is equivalent to saying that m is less than n to k minus 2 divided by k minus 1. Now, the conjecture of Hayakawa, Wojiech, and Rydl stated that if the reverse inequality holds, then asymptotically almost surely R does have the delta k Szemeredi property. And Hayakawa, Wojiech, and Rydl in 96 proved that this is true if k is equal to 3. So this is true for 3-term arithmetic progressions. Okay. So many years later, around 2009, this general theorem, so this conjecture was proved by Conlon, Gowers, and Schacht. So theorem, Conlon, Gowers, and Schacht. This is around 2009. This is true in much greater generality. All right. So what do I mean by much greater generality? So on Monday, I told you that one of the motivations for studying hypergraphs and independent sets in hypergraphs is that there's a natural encoding of these types of questions in the language of hypergraphs. So here we could just consider H, the hypergraph of k-term arithmetic progressions in 1 over n. And now this question reduces to the following. Let HM be the subhypergraph of H induced by this random set R. So here we have some collection of subsets of 1 through n. These subsets are the k-term arithmetic progressions. Now we keep a random set of m elements, and we look at all the progressions that remain. Now, within this hypergraph, we're asking what is the largest number of elements in a set which doesn't contain any k-term arithmetic progressions. Is it larger than delta times m or smaller than delta times m? So this question is equivalent to asking, is the independence number of this H R smaller than delta m? And very roughly, Conlon-Gowers and Schacht prove the following for a large class of hypergraphs. If M is sufficiently large, then the independence number of H will scale appropriately. Meaning, if I look at the independence number of alpha of HM, let's take the maximum independent set in H itself, then typically M out of n elements will survive. So we typically will have an independent set of this size, but in fact, if M is sufficiently large, then no larger independent set will appear. And this error here is little o of M. So in particular, in the case of arithmetic progressions, since the largest subset which doesn't contain any arithmetic progression has size little o of n, we get little o of m plus little o of m, which implies this argument. Now, the Conlon and Gowers and Schacht use very different methods to prove this theorem. Tammy Ziegler on Monday was speaking about methods related to what Conlon and Gowers did. But maybe let's try to analyze this question from a more combinatorial perspective. When would we know that this hypergraph HM doesn't contain any large independent sets? Well, if we take any independent set with this number of elements, then it's extremely unlikely to appear in the random set. So if we knew that there aren't too many such sets, then we could conclude this by using a simple union bound. So if we knew that the number of independent sets in H with more than m over n alpha of H plus now omega of m elements is small, then the union bound works. Now, it turns out that actually this is true in the setting of Szemeredi's theorem, and this is what I'm going to try to prove to you today. So this is true if alpha of H is little o of n. So for hypergraphs where the maximum independent set contains a positive proportion of the vertices, such statement is not true. But then one can still say that even though the number of independent sets is large, the number of independent sets which are vastly different is small, and then one can use a different type of union bound to conclude a similar result. So such a bound was proved by Yoshi Balog, Rob Morris, and myself, and independently by David Saxton and Andrew Thomason around 2012. So the theorem that we proved is fairly general. I mean, it doesn't apply only to this scenario, but to many similar scenarios. And so I'll state it in the widest generality, and then we'll derive a bound on the number of subsets of n of a given size which don't contain a k-term arithmetic progression. And this bound in particular will imply this theorem. So this is the plan for the remainder of today. So first, before I state the theorem, I need several definitions. So the setting will be, so H from now on will be some k-uniform hypergraph. Now, given such a hypergraph, what we're going to do first is generalize the notion of degrees in a graph. So now so let's denote the vertex set of H by V. Now, given a subset T of V, we will say the degree of T in H is just the number of edges of H which contain this set T. So if T is just a single vertex, then it's the usual degree, but we can also take a pair of vertices, a triple of vertices, and so on. And the maximum L degree of H will be the maximum over all sets of size L of the degree of T. Now, one more definition. So note that in the statement of this lemma counting the independent sets in graph, somehow we related their number to the number of subsets of the smallest set, of the largest sets which is almost independent. So we said that there was this threshold function R, and we assumed that every subset which has more than R elements already contains a non-negligible number of edges. So here we'll have a slightly more general condition. So actually for the application to Szemeredi's theorem, this slightly more general condition is not necessary, but for the application to describing typical structure of H-free graphs, which I will talk about tomorrow, this more general definition will be necessary. So what is this more general definition? We have some family F of subsets of the vertex set V. And now we also fix some positive number epsilon, and we will say that that H is F epsilon dense if every subset in F induces a non-negligible and epsilon proportion of all the edges of H. So think of F as sets which are large in H. So in our example, these are the subsets of integers which contain at least a quadratic number of k-term arithmetic progressions. Okay, now let me state the theorem. This is just the power set of V. So the theorem says that for every k and epsilon and c, there is a large constant c such that the following holds. Now here we let H be k uniform and F be a family of subsets of V such that H is F epsilon dense. Now we suppose that there exists some p, a real number p, such that for every L from 1 to k minus 1, the maximum degree, the L maximum degree of H is bounded by, here we have the average degree, C to P to L minus 1. So in particular, the maximum degree of H is only constant away from the average degree, but we also have conditions on all the other degrees which depend on this parameter P. So we would, this parameter P will show up soon in the conclusion. We're interested in making P as small as possible. So the smaller we make the P, the more difficult it is to satisfy this condition. Now, so once these conditions are satisfied, then there exist first a family S of subsets of the vertex set with at most C times P times C times P fraction of all the elements. So we have a family of fairly small sets which contain only a P proportion of the vertices, and two functions, a function G, which sends, so this is the family of all independent sets of H into this family S, and a function F, which sends every set in S into something which is not in F. And now the most important conclusion, the most important condition is that for every I, which is an independent set, I is sandwiched between G of I and F of G of I. Okay, so the statement is a bit technical and so maybe sounds a bit mysterious. So let me try to explain it to you in a picture. So let's here consider the power set of V. So these are the subsets of V ordered by inclusion. Now here on the top, there's the set V itself, and here on the bottom, we have the empty set. Now, we have this family F which contains sets which contain many of the edges. So we think of them as large sets. This is F. Now, on the other hand, independent sets are sets which are small. They don't contain any edges. So they will lie somewhere here on the bottom. Now, here, somewhere really, really low, we have the small sets which are in S. So this is S. And each set in S, this function F sends to something which is not in F. So we have this very tiny set contained. This is F of S, which is contained in the complement of F. Now, the conclusion is that whenever I look at some independent set I, then it is mapped here, this set is mapped here, and now this set I will be sandwiched between this lower set and this upper set. So in particular, since the number of such sets is very small, it means that I can cover the entire family of independent sets with very few sets. So such statement is not difficult because I could cover the family of all independent sets just by the set V. But what is important is that all these sets which participate in the covering contain very few edges. They're almost independent themselves. So roughly speaking, it says that all independent sets can be covered by a small family of sparse sets. So in particular, there can't be too many. Let's take R to be the minimum size of a set A over all A in F. Now, I mean the maximum over all sets which are not in F. So let's look at the largest set which is sparse. Now, since each independent set now is contained in one of the few sparse sets, then in particular, the number of independent sets is at most the size of S times 2 to the R. Because once we know in which element of the covering we are, there's only so many ways to choose the remaining elements. So in the setting of arithmetic progressions, we know that every subset which contains a positive proportion of all the integers will already contain many arithmetic progressions, which means that this size R will be only sublinear in N. So the number of sets which contain no arithmetic progressions will be very, very small. But this is just, so this is some of a very informal argument, and now let me make it slightly more formal. So the theorem that I'd like to prove to you is the following: for every k and beta there is a constant C and n0 such that if I take n to be sufficiently large and m to be at least some constant times n to k minus 2 divided by k minus 1, then the number of subsets of n of size m and no k term AP, this is at most beta n choose m, which is at most beta to the m choose times n choose m. So what does it mean? That among all n choose m subsets of size m, only a really, really tiny proportion of them, a sub-exponential proportion, are k-term AP3, once m is above this critical density n2, k minus 2 over k minus 1.
Which specific properties of this hypergraph is used?
So this is, yeah, that's a very good question. So this is only using the fact that every set of linear size contains a constant proportion of the edges. And also there's this restriction on the degrees. And for this problem, the restriction which determines the threshold is the one with L equals to k minus 1. Oh, sorry. The one with L equals k. I made a typo there. So if you, I mean, I'm really sorry, the statement here is really, really complicated, so I wouldn't be surprised if I lost you when I was describing it, but I hope that at least this statement is easy to comprehend, because this is just some statement about subsets of numbers. And I'll try to prove the statement now, but maybe first, before we prove it, I mean, it's maybe interesting in its own right, but let's see how it relates to this problem of having the Szemeredi property for random m sets of integers. And here the proof actually is very, very simple, just a simple union bound. Since the number of sets which contain no k-term arithmetic progression is so small, then constructing a set which contains a large subset with no k-term arithmetic progression, there's very, very few ways to do it. So there are very few such sets, so it's unlikely that the random set will have this property. So maybe let's write it down precisely. So corollary for every delta between 0 and 1 and integer k, there is a large constant C such that if m is at least a constant times n to minus 1, to k minus 2 over k minus 1, then the probability that a random m subset of n is not delta k Szemeredi is very small. It's at most E2 minus m. So with very, very high probability, a random m set will satisfy the Szemeredi property. So now proof. Well, let's just estimate this probability. If this M set fails the property, it means it has to contain a subset of size delta M and no k-term arithmetic progressions. So let's just take C sufficiently large so that the theorem applies for M replaced with delta M. Now, let's just count these sets. So out of all n choose M sets of size M, we need to count the ones which contain a large set with no k-term AP. So let's fix also beta to be delta over E squared times E2 minus 1 over delta. So I computed this beta so that we get this nice bound here. Now, the number of ways I can choose these delta M elements so that they don't form any k-term arithmetic progressions is at most beta n choose delta M by the theorem. Now, I choose the remaining elements in an arbitrary way. So this is just n minus delta M times M minus delta M. Well, this is at most beta to delta M times n choose delta M times n minus delta M times m minus delta M divided by n choose M. So this ratio, I mean here first I choose delta M elements, from the remaining ones I choose m minus delta M, so this is the typical exercise in counting. So this is exactly equal to beta to delta M times m choose delta M. Now, I will use the fact that A choose B is bounded from above by EA over B raised to the power B. So this is at most beta delta M times E M over delta M to delta M. And now my choice of beta was such that this computes to precisely E2 minus M. Is it clear? So maybe let's go through it again. I want to compute the probability that a random subset of size M doesn't fail this Szemeredi property. What does it mean to fail the Szemeredi property? It means that there has to be a set there, a large set of size at least delta, which doesn't contain any k-term arithmetic progressions. Now, I'll be overcounting, because maybe once a set fails such property, it contains many such subsets, but we only use the fact that it contains one. So by the theorem, this is the most important part here, this is the number of ways to choose this set of delta M elements. We really don't care how we choose the remaining elements, so this gives us an upper bound on the number of such sets, and we just divide it by the number of all sets. Now, beta was chosen to be a constant which is significantly smaller than delta, so that when I compute this ratio, I still get something which is very, very small. It's at most E2 minus M. So this is just counting. The only really important part is this. So this is the term which kills everything else. And this term comes from this theorem. So let me say a few words about the proof of how to derive this theorem from this theorem about characterizing independent sets in hypergraphs. So there are two ingredients here. First of all, I mean, it might, let's look at this statement. And suppose that I take m to be linear in n. If I take m to be linear in n, then the theorem will tell me that, if I say take a to be 2 beta n, then this theorem will in particular tells me that there are 0 sets which contain 2 beta n elements in no k-term arithmetic progressions. So this implies Szemeredi's theorem. But as you know, Szemeredi's theorem is a very difficult theorem, and I'm not claiming that I have proved it. So I better use the statement of Szemeredi's theorem as a black box when I'm proving this statement. So indeed, this is what we will have to do. So there are two ingredients here. So first ingredient will be just analyzing the hypergraph of arithmetic progressions and computing the bounds, all the maximum degrees, to determine this parameter p, which will determine that this is the right threshold to look at. And there will be a second ingredient which will involve the proof of Szemeredi's theorem, which will help me to describe this family F. So I need to identify this family F, the family of sets which contain quadratically many arithmetic progressions, as the family of sets which contain only any positive proportion of the elements. And in order to prove that this family F could be taken as the family of all sets with at least, say, delta n elements, for this I will need to use Szemeredi's theorem as a black box, because I mean, I'm not claiming that I'm able to give a nice proof of it. Okay, so let's start with the easier part. Let's start with analyzing this hypergraph of arithmetic progressions. This is just a warm-up. So let H be the K-uniform hypergraph of K-term APs in the set 1 through n. Now, how many edges does it contain? It's order n squared, because I have only 2 degrees of freedom, the starting point and the difference. Now, what is delta 1 of H? Given an element, how many arithmetic progressions does it contain? So can it be contained in? It's at most a linear number, because given an element, I can just choose which position does it take in the arithmetic progression and what is the common difference. So this is an upper bound. Now, delta 2, I give 2 elements, and how many arithmetic progressions can contain these 2 elements? Well, it's enough if I say that one is position I, the other is position j, so it's at most k choose 2, and in fact, this is a bound for all larger degrees, because if I take any larger set, then it contains some 2 elements, and these 2 elements already give me a bound, and I mean, for all purposes, this is just a constant, so I can't do any better. And so now let's check the condition. So the condition was that for every L in 1 up to k, this delta L of H had to be bounded by a constant times p to L minus 1 times E of H divided by V of H. But in our setting, the number of edges is n squared, the number of vertices is n, so this is just C p to L minus 1 times n. So this is the condition we need to check. Now really there are just two values of L we need to consider, because the higher L, the more difficult it is to check. So among all the 2L from 2 to K, I just need to check the last one because it gives the strongest condition. And for L equals 1, as I said, this is just comparing the maximum degree to the average degree. But the average degree is n, and the maximum degree is also n. So we only need to check that delta K of H is at most a constant times P to the K minus 1 times n. And delta K, it's the maximum number of K-term arithmetic progressions that some K numbers can be contained in. So of course this is just 1. So this is equivalent to saying that P is at least n to minus 1 over K minus 1, and hence this family S will be contained in subsets which contain at most P times n elements, which is constant times n to K minus 2 divided by K minus 1. So this is precisely where I get this this threshold value here, because below it, I mean actually it's not hard to convince yourself, and I'll do it tomorrow in a different setting, that below this threshold this theorem is not true, because if we're below this threshold, if we put a small constant, then I can prove that this is the case. So this is just a simple deletion argument. Okay, and now there's another ingredient here, which is, so I already characterized this family S, so I know what number of sets I will use for the covering, but I would also like to say something about these covering sets. And this is the part which is really relevant to the problem we're working on, right? Because the theorem only tells me I can cover all the independent sets with sparse sets, and in order to deduce any meaningful information, I need some description of the sparse sets. Szemeredi's theorem gives me a description of independent sets, but actually in many instances, from a description of just independent sets, I can derive a description of sparse sets using an averaging argument, and I'll give an example today. And once you see one or two examples, somehow it becomes clear how to do it. So deriving characterization of sparse sets from independent sets uses this sort of symmetry and self-similarity of the problem. It will be clear in a second. Unfortunately, maybe the setting of H-free graphs is much easier to deal with than the setting of K-term arithmetic progressions, but nonetheless the argument is not too difficult. So what should I erase? Maybe here. So the goal is the following: characterize sets A in N which have omega of n squared K term arithmetic progressions. So Szemeredi's theorem tells us how to characterize the ones that have one. Sorry, I should write little o of n squared here, because we're actually interested in the complement of the family F, not the family F itself. So I want to characterize sets which have few arithmetic progressions. Szemeredi's theorem tells me that if I replace this condition with 0 arithmetic progressions, then I know that these sets are small. But now there's a general principle here, and I think it goes back to the work of Varnavides, who proved the following, that actually Szemeredi's theorem is true in a stronger sense. Once I have a positive density of numbers, then not only I have one arithmetic progression, but I have order n squared arithmetic progressions. This statement is as follows: for every positive delta and integer k, there exists epsilon greater than 0 such that for sufficiently large n, of every set of the first n integers, which contains a delta proportion of the numbers, it also contains a positive proportion, epsilon n squared arithmetic progressions. Okay, so let's prove it. The proof actually is not so difficult. So here we will fix some m, which is a constant, and m is around n0 of delta nk. This is the smallest number where Szemeredi's theorem applies. Right? Szemeredi's theorem applied only if the number of integers is sufficiently large, and I take the smallest such n for a given delta nk, and this is just for all purposes some constant. It won't be a very small constant, but it's just a constant. Actually here, sorry, let me take delta over 8. Now I'm given an n which is much larger than m, and I fix a prime p between 2n and 4n. And I'm going to work modulo p. So here, let's draw zp. And somewhere here lies the interval 1 to n. Everything ends before p over 2, and I mean p needs to be larger than 2n so that I don't have any arithmetic progression which wraps around and is not an arithmetic progression in the original setting. And now let's x and d be two numbers from ZP, d not 0, and I choose them uniformly at random. Yeah. Oh, yes, prime. Yes, so we also write probability in this way. So. Okay, so I choose two elements of ZP uniformly at random. And now I just consider the progression which starts at x with common difference d of length m. So x plus d, x plus 2d. It can wrap around many times. But let x just be x plus d, x plus m minus 1 over d. Now, this is I mean, this is just an arithmetic progression of length m. So it's for the purposes of finding arithmetic progressions, this is isomorphic to the interval 1 through m. So this is my self-similarity here that I was referring to before. And note, since the elements x and d were chosen uniformly at random, then every element of ZP is covered by the set X the same number of times. So in particular, when I look at the expectation, the expected trace of A in X, then this is exactly equal to A divided by P times M, which is at least so P is at most 4n, and A is at least delta. So in particular, if I take any set A which has at least delta n elements, then the trace of A on X will be A over P times M, which is at least delta M over 4. Right, so it's on average, it's also a delta proportion of the set X. And now, within the set X, I want to apply Szemeredi's theorem. But here, this is just a statement about expectation. So I need to also conclude that with some probability, I will see a set which is dense. But for this, we can just use Markov's inequality. So you have even something simpler than Markov's inequality. So suppose this is all the choices of X, and certainly A intersection X cannot have more than M elements. So with probability, this is the worst case scenario. So with probability at least delta over 8, X intersection A has at least delta over 8m elements. So with probability delta over 8, I can apply Szemeredi's theorem, which means I find one arithmetic progression there. So the expected number of arithmetic progressions in my set is delta over 8. Hence, by Szemeredi's theorem, the expected number of k-term arithmetic progressions in A intersection X, it is at least delta over 8. But there is another way to compute this quantity. Right? Now let's use linearity of expectation. For every fixed arithmetic progression in A, there's some fixed probability that it survives choosing these elements X and D. So this is equal to the number of k-term APs in A times the probability that this given k-term AP is contained in X. Now, I will upper bound it by saying that this is the number of k-term APs times the probability that given two elements A and B belong to X. This is clearly an upper bound. And by symmetry, I can assume that this is just 0 and 1. And now, so number of k-term APs in A times the probability that 0 belongs to X times the probability that 1 is in X, given that 0 is in X. So this is just M divided by n by symmetry. And if you think about this, if I require my set to contain the element 0, then still under this conditioning, each remaining element will be covered the same number of times. So this probability here is just m minus 1 divided by n minus 1. Okay, and if I now compare this to that, we conclude that originally, since this expectation is so high and each arithmetic progression survives with the tiny probability, then actually we needed to have lots of them. So the number of k-term APs in n is at least n times n minus 1 divided by m times m minus 1 times delta over 8. And for all purposes, this was a constant. I mean, this is now a tiny constant, but nevertheless a constant. So this is omega of n squared. So if you're familiar with the proof or with any proof of a supersaturation theorem for Turan's theorem, this is more or less, I mean, morally this is the same idea. The problem is, why this is somewhat more difficult is that in the setting of graphs, if I look at the graph on n vertices, then every subset of given m vertices looks exactly the same. And here it's not true. I mean, in order to make this averaging work, I need to cover my set with sets which are of the same type and are smaller. And here, if I try to do it with the interval, I run into all sorts of problems because, I mean, the elements are not symmetric. That's why I have to move to the circle here. So actually, I would still need around 15 minutes to derive this counting statement from these facts that we have already established. So maybe let me postpone it until tomorrow.